Feature importance with MLJAR. We have seen that the model we created with AutoML was able to perform a binary classification task reasonably well. But why did it make the predictions it did? Which of these features were the most predictive? To answer that question, we can look at the feature importance for each model. The data on the feature importance is automatically saved for each model, except the ensemble, which is a weighted combination of other models, when the models are trained. Let's take a look at the feature importance for the best individual model that AutoML found, the random forest. Two different feature importance metrics are reported, the permutation feature importance and the SHAP feature importance. Permutation importance of a feature measures how sensitive the prediction of the model is to changes in the value of that feature. That is, how much the prediction changes if the value of a feature is varied, and you can see this on the plot on the left. SHAP, Shapley Additive Explanations feature importance, tells you to what extent the prediction of the model can be attributed to any individual feature. It's based on game theory. And we'll have a look at this later in more detail. We can see that the permutation feature importance and the SHAP feature importance do not always agree on the relative importance of the features. The SHAP feature importance is the more reliable metric and is the one you should trust more when interpreting your models. Now let's understand a little bit more about the SHAP feature importance plots. The SHAP feature importance plot shows the relative importance of each feature for the predictions of the model. However, it does not say anything about how each feature affects the model's predictions. Is the correlation positive or negative, linear or non-linear? A more detailed understanding of each feature's effects can be developed based on SHAP dependence plots. Here are the SHAP dependence plots for the random forest model that predicts the survival of Titanic passengers. Each dot is a singular prediction from the dataset. The x-axis shows the values for the feature considered. The y-axis shows the SHAP value for that feature, which represents how much that feature's value changes the output of the model for that sample's prediction. The color corresponds to a second feature, chosen automatically by default, that may have an interaction effect with the feature plotted. If an interaction effect is present, it shows up as a distinct vertical pattern of coloring. For instance, from the plot for the feature P-class, passenger class, we can see a positive effect in first or second class on survival and a negative effect of being in third class. The color-coded feature for this plot is sex, and one can see that the effects of passenger class on survival are present for both men and women, but are much more pronounced for women. One can also see that the range of SHAP values for women in first class is smaller than the range for women in second and especially in third class. Therefore, the passenger class is a considerably more reliable predictor of survival for women traveling in first class than for women traveling in second and especially in third class. Now for your own learning, as an exercise, try performing a similar analysis of the SHAP dependence plot for age. In this section, we have seen that the SHAP feature importance is very useful for understanding which features are the most important predictors for the target variable and how exactly each feature affects the target variable. Let's try to develop a basic intuition behind SHAP feature importance so that you have a better understanding of what exactly it measures. Shapley values. Imagine that we have an ML model for predicting apartment prices. For a certain 450 square foot one bedroom on the second floor of a building near a park where pets are banned, it predicts a price of $200,000. The average predicted price for all apartments is $280,000. How much did each feature of our specific apartment contribute to the difference of its predicted price from the average prediction? For a linear regression model, the effect of each feature is the weight of that feature times the feature value. For more complex models, it's not that simple. In 1953, Professor Lloyd Shapley suggested a method that can be used for determining feature importance that is based on game theory. He considered the problem of distributing winnings between several cooperating players in a game based on their individual contributions. Translating this approach to machine learning, the game is the prediction task for a single instance of the dataset. The gain is the actual prediction for this instance minus the average prediction for all instances. The players are the feature values of the instance that contribute to the prediction. In our example, each feature, for example, total area, number of bedrooms, floor, proximity to the park, and banned pets, somehow affects the apartment price. We need to figure out the contribution of each feature to the difference of the predicted price, $200,000, from the average price, $280,000. For example, the total area of 450 square foot is smaller than average, which has a negative impact of $50,000. There's one bedroom, which is fewer than average, which has a negative impact of $40,000. It's on the second floor, which has zero impact. It's near the park, which is desirable, which has a positive impact of $20,000, and pets are banned, which is undesirable and has a negative impact of $10,000. Together, these contributions add up to a negative value of $80,000. The Shapley value is the average marginal contribution of a feature value across all possible coalitions. Let's see what that means in further detail. Let's say we want to calculate the Shapley value for one feature, the pet ban. We have 4 other features, and therefore can consider the following 16 coalitions or combinations of features. For each coalition, keep features in the coalition fixed. Pick features not in the coalition by randomly drawing another apartment from the dataset and using the values of those features for the drawn apartment. Number 2. Now predict the price for the apartment thus sampled twice. First, keeping the value of the feature of interest, pets banned, fixed, then taking the value of the feature of interest, pets banned, for the randomly drawn apartment. 3. Take the difference between these two predicted prices, the marginal contribution of the feature. Note that this difference depends on the features of the random apartment drawn. 4. To increase accuracy in the estimation of the predicted price differences with the features of interest fixed and randomly drawn, repeat the described steps, setting features not in the coalition to values for other randomly drawn apartments. Then find the average marginal contribution. The Shapley value is the weighted average of the marginal contributions for all possible coalitions. By estimating the Shapley values for all feature values, we can get the complete distribution of the prediction, minus the average, among the feature values. Take a minute to review these steps to make sure that you understand them correctly. Congratulations for making it to the end of this course on AutoML. We'll now go through a summary of learning outcomes. 1. An introduction to AutoML. We took a basic overview of what automated machine learning is and how it works. We also learned about AutoML advantages and its limitations, as well as the variety of tools available. In Section 2, using AutoML with scikit-learn, we first looked at classification with AutoSKLearn. We used the make classification function to generate a synthetic dataset, split the dataset into training and test sets with train-test-split, and build a classification model using the AutoSKLearn classifier object of AutoSKLearn. We then used accuracy score to evaluate the model's performance, and printed various information about the model with the leaderboard function. Following this, we also looked at regression with AutoSKLearn, and followed essentially the same steps as the classification pipeline, but for a regression pipeline. In the third section of this course, we looked at end-to-end AutoML frameworks. Firstly, we looked at exploratory data analysis with MLJAR. In this, we performed exploratory data analysis using the EDA object of MLJAR, and used the readCSV function to read in the dataset in CSV format. We visualized the data using the extensive EDA object. Secondly, we built a machine learning model with MLJAR. We made this machine learning model using the AutoML object of MLJAR, trained it using the fit method, and predicted for the test set using the predict method. We then calculated the accuracy of our model's predictions with the scikit-learn accuracy score function. Finally, we looked at setting AutoML parameters. We learned about important parameters used in the AutoML object, such as total time limit, model time limit, algorithms, train ensemble, eval metric, and validation strategy. In the fourth section of this course, we looked at feature importance with MLJAR. In this section, we looked at Shapley values and also took a deep dive in order to get an intuition for the meaning of Shapley values. We also looked at permutation and SHAP importance, and we also understood how to identify significant features and their effects on the model's predictions using SHAP feature importance and SHAP dependence plots. We've now come to the end of this course. Thank you very much for joining, and I hope you enjoyed it. Should you be interested in learning more about what was covered in this course, please look at the references in the following slide.